Hi, I'm Young-Sun from Purdue University. In this talk, I would like to introduce our work, Market Equilibrium in Multi-Tier Supply Chain Networks. This is joint work with Tao and Tan. I'll start with the intro, including the graph of interest, what kind of equilibrium that we're trying to solve, and what's the decision model, followed by our main results, which includes the main theorem and some structural analysis. So, for the main prior literature, what were studied were two types of specific graphs, namely bipartite graphs and line graphs. In the bipartite graphs, there are two parts, where one side consists of source producers, and the other side consists of ending markets. Each source producer has a cost to produce something and sell some goods to each ending market. So the source producer makes a decision on the amount to produce and the amount to sell to each ending market. And the objective of each source producer is to maximize its utility. On the other hand, an ending market has a price that's related to the total incoming amount of goods. So at an equilibrium, all the source producers simultaneously makes their decision. And if it's the case that none of the source producers are willing to change, then that's a competitive equilibrium. For a line graph, it actually captures the case that all the upstream firms have to make decision to maximize their utility. And the assumption is based on the fact that all the downstream firms are going to act adaptively according to the upstream firms, and also maximizing their utility. So this captures the subgame perfect equilibrium. So our question is as follows. Is there any kind of graph that captures both of the main ingredients, namely competitive equilibrium and subgame perfect equilibrium? So our answer is yes. Specifically, we study series parallel graphs termed SPG. So a series parallel graph is constructed inductively, where the base case is just a single edge. For the inductive construction, it is either by series composition or parallel composition. For series composition, we're given two series parallel graphs, and we just concatenate them. While for parallel composition, we're given two SPGs, and we place them parallelly by merging the sources and the sinks. So for series parallel composition, it sort of captures the increase of a length in the trade. And this corresponds to sequential decision making. While for parallel composition, it denotes the increase of competition. So it sort of captures competitive equilibrium. So that's our motivation behind for studying series parallel graphs, because it sort of captures the two main ingredients. So here I would introduce what's the sequential decision model. Suppose we're given a DAG, single source and single sink. For the source, there's a production cost, AS, which is a positive constant. And this cost is the price per unit. On the other hand, for the sink, there's a price function that is affine decreasing in terms of the total incoming amount of goods. Here, AT is at least AS, so that we're guaranteed that the ending market price is at least the production cost. And this ensures that there will be some trades going on. In the beginning, S produces excess amounts of goods and pays AS times excess. So after producing, S offers U some quantity of goods with a price. And this quantity is termed XSU superscript out. So later, whatever superscript out, it means the quantity that's offered from the upstream. Similarly, S offers V some amount of goods and the price. And we note that the total offering amount to the downstream cannot exceed the produced amount by S. So the decision of U is how much to buy from S. This is termed XSU superscript in. So whatever superscript in, it denotes the accepted amount. And we note that the accepted amount cannot exceed the offered amount from the upstream. And it's similar for V. So now, having all these values, we are able to derive the utility of S. So the utility of S is basically the revenue obtained from U and V minus the production cost. Okay, so the decision making just keeps go on and on to the downstream. Now U offers V some quantity of goods with a price. Again, the quantity cannot exceed the amount accepted from the upstream. Accepted from the upstream. And same thing for V. So W is going to accept something from U and V. Now we are able to derive the utility of U, which is basically the revenue obtained from W minus the buying cost from S. And same thing for V. Now at the last stage, W will offer T some quantity of amounts, some quantity of goods, which is upper bounded by the total amount accepted from total amount obtained from U and V. So we assume that the ending market T accepts everything from its upstreams, and the price is just an affine linear function of a fine decreasing function in terms of the inflow. So the price it's in terms of how much W is going to offer to T. And eventually we can derive the utility of W, which is the revenue obtained from T minus the cost from U and V. When W is done with its decision making, then this game is done. So let's be a bit more formal. What are the decision variables of each firm? So for each firm I, we consider two sets, SI, which denotes the set of selling firms of I, and BI, the set of buyers of I. So each firm I decides three variables. The first one is the buying quantity from the upstream. So for S, it does not really have this decision variable. Instead, the decision variable is the producing quantity. And the second decision variable is the selling quantity to the downstream. The third one is the price. We recall that the amount offered has to upper bound the amount accepted, and the ending market T just accepts everything. Okay, so we have our decision variables defined. What's the utility of a firm? So the utility of a firm consists of two components, the selling revenue and the buying cost. So the utility of the firm I is just the selling revenue minus the buying cost. For the selling revenue, it's a sum of products of the price and the amount. And the buying cost is similarly defined. The utility of S it's defined in a similar way, except that the cost is replaced by the production cost. Now we're ready to define what's an equilibrium. So in an equilibrium, whatever is offered must all be accepted. That means no goods are going to be rejected. And it also means the upstream will not oversell anything to the downstream, so that they will lose something by overpaying. So it's the case that xij out is the same as xij in. And later we'll just denote them as xij. So at equilibrium, flow conservation should also hold. So this means for each firm, the inflow is the same as the outflow. So this is based on the assumption that each firm will not obtain utility by retaining goods for themselves. Now, for each firm I, the objective is to maximize its utility. And we say that at an equilibrium, each firm does not have the incentive to change its strategy based on two assumptions. First, each descendant firm of I plays the best according to the upstream. And second, the strategies of non-descendant firms remain the same. So this is for each firm I. So if this holds for all I's, then we say that it's an equilibrium. So let me be clearer. Suppose let's consider the previous example. So in this example, from the point of view of W, the upstream decisions are all fixed. So W will just buy something from U and V, and then sell something to T. And W is trying to maximize its utility. From U's point of view, you assume that W will play adaptively, and at equilibrium, U is not willing to change its strategy, assuming that S and V's decisions are fixed, and W plays smartly. So the point of view of V is the same as U. It's just symmetric. While for S, it assumes that U, V, and W, they will all play in a smart way, as aforementioned. So at an equilibrium, S, U, V, and W, all of them are not willing to change its strategy based on the two assumptions. Okay, now we reach our main results. So there are two main things, the main theorem and structural analysis. So for the theoretical part, namely the main theorem, we show the following. For series parallel graphs, there exists a linear time algorithm that finds the equilibrium, and the equilibrium is unique. And this is done by an algorithm that consists of two steps. First, the backward price computation step, and second, a forward flow computation step. Intuitively, when we're trying to solve subgame perfect equilibrium, it should always be the case that the upstream is considering some nice strategies behave by the downstream. So it's always done in a backward manner. So to do the backward price computation, we derive a very important lemma that kind of relates the price and the quantity. So for this lemma, it says for series parallel graphs at equilibrium, all the edges are active, meaning there will be some positive trade flow for each edge. And each seller of I, so K in Si, each K offers I the same price. So the price is in this form. PKI is an affine decreasing function. It's in the form of AT minus some linear combination of the inflow of some merging downstream nodes. Here, BI are constants that only depends on the graph structure. So we take advantage of the structure of series parallel graphs. Suppose we focus on a specific trade I to J, then it must be one of the following three cases, SS, MS, and SM. So for SS, it denotes the case that there's a single buyer and a single seller. And MS and SM are defined similarly. Basically, a multiple seller and single buyer, and single seller and multiple buyers. So the high-level idea of the backward price computation is as follows. We start inductively from the sync market in the reverse topological ordering. And the base case is just an affine decreasing function which clearly holds. When we reach an SS case, we start from a point of view of firm I. And suppose by inductive hypothesis that the price function holds for the buyer J. So what we do is plug in the price function of J into the utility function of I, and we have this form. A nice observation is that this utility of I is actually concave in terms of the variables xki. So basically, the utility it's a quadratic function where the quadratic terms have some negative coefficients. So what's good about concavity is that if we take the partial derivative of it, and if it's zero, then that means the variable xki should be optimal. So we take the partial derivative, and we derive a linear complementarity problem termed LCP. So let's take a look at the second constraint of LCP. Basically, it says that the partial derivative has to be non-positive. Suppose it is positive, then what firm K can do is to raise the price PKI such that the partial derivative becomes zero, which means the decision of I should be optimal. And this contradicts to the assumption that we're under an equilibrium. While the third constraint, it's basically saying that the flow has to be non-negative. The first constraint is a sum of products, where each product of the partial derivative in the variable. So for the partial derivative, if it is negative, that means if there are some positive trade flow on this edge ki, then the utility will just decrease. So it should be the case that if the partial derivative is negative, then there is no flow. And by summing it up, the value should be zero. And that's how we get the first constraint. So from the LCP, we can conclude that if the trade K2I is active, then the price PKI is such that the partial derivative is zero. And from this, we derive a closed form for the price. The analysis for the MS case, it's quite similar. So we just plug in the price function into I's utility function. And by concavity, we take the partial derivative and derive LCP. Again, we claim that when Ki is active, then the price should be such that the partial derivative is zero. And we get a closed form. The most interesting case is the SM case. So in this case, we recall that the utility of I it's denoted as the revenue minus the cost. And at equilibrium, we observe that I does not really have control over the buying cost. And that's because I will just accept everything at equilibrium. So instead, we can focus on maximizing the revenue. By this, we derive a convex quadratic programming as follows. So the objective is to maximize the revenue, subject to by distributing the flows xi to j, and the sum has to be the same as the inflow. So here, capital C denotes the amount of inflows that goes to I. The decision variable, it's really just how much goods I is going to assign to each j. So by doing some math and the Lagrangian function, we show that this is equivalent to solving a system of linear equations. And this can be done in linear time from the structure of SPG. Moreover, the optimal strategy of I is to scale proportionally to the convex coefficients alpha ij, where all of them are positive and can be derived by a closed form. By plugging in proportionally to the convex coefficients, we are able to derive a closed form for the price. Since each convex coefficient is positive, this also implies that each trade ij is active. And from the structure of SVG, whenever some of the flows are branched, eventually it will merge somewhere. So this also implies that all the edges in the network are active. Last but not least, the uniqueness of the equilibrium is by the convex quadratic program. Okay, let's summarize what backward price computation was doing by a simple example. So suppose we're given this instance, we have the price at the ending market. We do induct, we do by reverse topological ordering. So we have a price for T, then we have a price for W, and this is the SS case. And for the case UV to W, this is MS case. Eventually, when we reach S, this is the SM case. And we want the price of S to meet the production cost. So we solve the total flow by doing this. And once we obtain the total flow value, then we're done with backward price computation. After having the total price value, here comes the second part of the algorithm, forward flow computation. So for forward flow computation, we start from S by topological ordering and assign flows as follows. So for the SS and MS case, since there is only one buyer, the decision for the seller is just offer everything to the buyer, and there's no other decision. So the interesting case is actually the SM case. However, most of the heavy work were done before, which was basically calculating the convex coefficients alpha ij's, and we just proportionally assign flows according to those convex coefficients. So we start from S, and since this network is symmetric, the convex coefficients should be half and half for SU and SV. Therefore, we assign 1 unit of flow to U and 1 unit of flow to V. This is the SM case. Now we reach an MS case. So U and V just assign everything to W. Eventually, we'll reach an SS case, and W just assigns everything to T. Okay, we're done with our main theorem. Now, from the main theorem, we're able to derive a rich set of structural analysis. We start from two aspects. First, the local aspect, and second, the global aspect. So for the local properties, we discuss the firm location and individual utility. While for the global properties, we discuss how the components can affect can affect the equilibrium. So we discuss firm location and individual utility. We say that firm I is a dominating parent of J if all the flow from source to J must go through I. So in this case, the red node A is a dominating parent of the blue nodes. From the closed form, we obtain the result that the dominating parent has at least twice as much utility as each of the dominated firm. So in this example, the utility of A is at least twice of the utility of B. It's also at least twice of that of C, and so on and so forth. Especially for the SM case, the dominating parent has at least twice as much utility as the sum of all the buyers. So in this case, the utility of A is at least twice of the sum of B, C, and D. So for a global perspective, we focus on two criteria. That is flow efficiency and welfare efficiency. So we say that an SPG is more flow efficient if it has a higher flow value. And SPG is more welfare efficient if it has a higher social welfare. So the social welfare is the sum of individual utilities of each firm plus the consumer surplus. We show that from the closed form. Suppose the source production cost and the ending market price both are fixed. Then if we swap the order of the series components, then the flow and welfare efficiency will not change. So by swapping them, the efficiencies are the same. Again, suppose the source production and the ending market price both are unchanged. Then if we do some series composition, what happens is that the flow and the welfare efficiency will decrease. And intuitively, this is because with multiple degree marginalization, the efficiency just goes down. While for parallel composition, suppose again the source and the sink they have fixed price and production cost, then what happens is that the efficiency will increase, and this implies the increase of competition will just increase this. It will just make the efficiency increase. Everyone will get more, basically. Okay, let me conclude here. So what we studied was market equilibrium in series parallel graphs, and we showed that the equilibrium is unique and can be computed in linear time. We also study equilibrium comparative statics. Although not listed in this talk, we do have results for multi-terminal SPGs, and we show that equilibrium may not exist, or it can be the case that there exists multiple equilibria. So I'll end with very interesting open problem. So the open problem is to find the equilibrium in general DAGs. And a bit surprisingly, even in very simple DAGs that are not SPGs, there can be traits that are inactive. I'll end my talk here. Thanks for your